today I'm going to talk about mechanics with artificial intelligence, and I'm going to browse through some of the recent advances in AI and how essentially AI can help us to solve some of the challenges in mechanical engineering. So if you think about it, the recent advances that we have in AI and machine learning, all of them, most of them are essentially rooted in this amazing paper that came in 2012, which is called, AlexNet, in which for the first time, a few great pieces of advances like convolutional neural networks, training on the GPU, technologies like dropout have been actually introduced to the field of AI and machine learning and totally revamped the path of essentially AI. And the story is that millions of images were able to be classified using convolutional neural networks into into 1,000 classes. And that's something very difficult using hand featureization and essentially using the features that are only pixels or computed features. So in summary, I wanted to talk about two of the most important revolutions in AI and machine learning since 2012. And with using those two revolutions, I'm gonna talk about what we can do and what are the opportunities for us as mechanical engineers to advance the field. So the first, I think, revolution is this automatic feature detection and learnable filters. As we know, like a human being is understanding and figuring out images and vision using a cognitive sense in which we see things holistically and we are not looking only at individual pixels. For example, this swan that is pretty much deflected, still we can say it is a swan, or this cat, or this cat that is in the dark. And the reason is that the way that we see is quite different from the way that the computer actually sees these images. And then this mechanism of convolutional neural networks, that there are learnable filters that they can learn over the features that are multiple layers or multiple levels of features like edges, or for example, the distance between eyes, or whatever is needed in order to boost the accuracy, I think is the first revolution that happened since AlexNet paper in 2012. The second big revolution that I think happened was back in 2015, in which we were able to combine Q-learning or reinforcement learning with the deep neural networks. In other ways, with the great paper that came out about human level control through deep reinforcement learning in Nature in 2015, they have showed that essentially you can play all these Atari games using deep reinforcement learning. And this is traditionally one of the big problems that a state space, when it goes to very high level, like 84 by 84 by 4, it's not handleable with shallow machine learning or traditional machine learning techniques. So combining it with deep neural networks in order to approximate the function that is here was a big deal back in 2015. So these two revolutions, I believe, are really big. One of them CNN and another one DRL. And some of you may wonder that why we are using AI and ML and what is the utility of AI and ML. So in engineering and in many tasks in real life, we have very, very difficult mapping or complex function. Essentially, for example, if you think about predicting the property of a molecule, for example, you want to predict the property or of this molecule, take, for example, solubility, it's very difficult. There's no mathematical or there's no physical, essentially, description that you can write the math or you can write the equation to connect these two together. So in these cases like this, and then cases like this, that you have an image and then you want to write, for example, the caption for this, right? So these are very difficult and complex mapping. And since we don't have a great, intuition or essentially mathematical / physical understanding, AI or machine learning can be very useful. How it can be useful, essentially you create a training set and then you train a machine learning or AI algorithm. And after that, you can test it on the new test set or new samples and find out, for example, or predict the solubility of this molecule that hasn't ever been seen here. Or for example, on the right side, you can train, for example, X and Y, X to the Y, which X is an image, and then there is a caption, and then essentially you can predict the caption for this image that is here. And this is the amazing world of AI, in which it gives us this complex manifold of essentially mapping that is possible. So, okay, now we know that this is very interesting, this is very exciting, and there are a lot of possibilities. But what are the possibilities for a mechanical engineer? How can we use this in our essentially research as a mechanical engineer, or as a tool chain, or as a kind of tool in our work or in our job? So to me, I think, these are a few bullet points in which I think, we can have impact. So complex phenomena in mechanical engineering that we don't have mathematical description. And the second thing is that where we don't know the physics, but we want to predict to engineer. For example, as I mentioned, for the molecular machine learning or for material science, we don't know really the physics, the complex physics, but we can use AI in order to predict. And we need, prediction, because we need to engineer the systems. Where we want to speed up computation by surrogate fast models, we know that we are running finite element analysis, we run computational fluid dynamics, but the speed of them might not be that much actually great in terms of computation, and we want to have a faster compute. And then essentially AI is able to learn the redundant computation or patterns and essentially surrogate them. Where we have abundance of data from experiments and want to make a more precise model. So we know, for example, for the cases of turbulence or in robotics or in manufacturing, we have a lot of different models. For example, we have convection model for heat transfer, we have conduction model, we have Navier-Stokes equation, which is describing fluid mechanics. We have also diffusion osmosis type of equation. But these models are not essentially a great model that they can be fitted into the real experiments. There's always noise with the data, and there is some kind of other complex phenomena that we might not be able to model them. So in these four categories are really important, and you can find out examples in fluid mechanics, in solid mechanics, bioengineering, dynamic and control, and material science. So I will go over really immediate impact of AI in mechanical engineering, and what I call usually, and I talk to my students as low-hanging fruit stuffs that you can do. For example, the simplest thing that you can do using, which is very, very useful essentially, is to apply, for example, existing networks that are there in order to classify parts that are manufactured using additive manufacturing. For example, here, as you can see, there are different parts that are manufactured using 3D printing and laser powder bed fusion at CMU. And then you can see there are different level of spatter. For example, a spatter level 1, which is 0, which is no spatter, some spatter, and too much spatter. And as you know, a spatter is not a good phenomenon for having basically parts. So you can use, this gallery of different CNNs in order to classify, different parts into different level of defects. And that is helping you for certification of parts, for essentially quality assessment of the parts, or even for adjusting the processing parameters in order to avoid such kind of defects. So this is immediate because, I mean, there are a lot of classification algorithms like VGG16, ResNet, MobileNet. You can develop and rewire the whole custom CNN. But what we can do in order to do much more advanced actually use of AI in the systems that we have in mechanical engineering, I'm gonna just quickly go over 3 examples. So the first example will be PDE discovery, or what we call system identification, in which you have a time-dependent time series of data, and you wanted to find or extract the partial differential equation. The second story will be about material discovery. As I mentioned, this is a very difficult task because, I mean, materials, they have all these different elements inside them, different organizations and structure. So how AI can help us in order to predict, and also in additive manufacturing and control. So the first topic is about system identification and PDE discovery, in which, as I mentioned to you, you have a time series data, and then you wanted to essentially assemble the partial differential equations by assembling each of these terms that are related to this time-dependent spatial phenomena in 2 dimensions. You can extend this also into 3 dimensions. So what we did here in this paper, which is available, and the code is also available on the GitHub page of the lab, is that you can extract features. So you can do feature engineering, in which essentially you can go over the data, the time-dependent data, and extract some time derivative or space derivative features, and then use ensemble methods like XGBoost to make a decision that what kind of terms, for example, should exist in the PDE. So we created a data set combining all different possible partial differential equations that they have different terms with first derivative, second derivative, convective terms, and we assemble them together with different coefficients. So the coefficients, for example, C or B or BY are changing, and this data is normalized, so you cannot basically distinguish them based on their color. And the task is that can we somehow reassemble them together? So we extracted some temporal and spatial features out of the data, in which, for example, you can be innovative in that way and think about it, for example, for the Laplace equation that don't have any kind of time-dependent data. If you subtract 2 consecutive frames, what we will get will be a 0 signal over all the frames. But for example, for the wave equation, you can get something like this, or for the heat equation, since there's a damping factor, you get something like this. So these are the signatures of time-dependent spatial data that you can get out of time. Also, you can get a lot of different kind of features from the space. There's something that we define using mathematical formulation as called motion vector, to distinguish the features that are hidden and to distinguish between convection and diffusion, because these 2 things, especially at the low level of convection, it might be hard to detect. It might be difficult to detect essentially if there is a convective term inside the PDE. So we created something called motion vector, in which we are finding the asymmetry in the data. For example, if the data is symmetric for the motion vector, you can understand that there is it's a diffusion only. But if the symmetry is broken, you can think of it as a convection. So we trained using this data. I mean and extracted the features, and we trained different XGBoost models. And one thing that is important in the training and essentially testing is to really be honest in terms of the validity and validation. So one thing that is very easy to do is to essentially create and test these learned algorithms on some of the PDEs that already are known, but the coefficient is different. But we didn't do that. So we completely put one class of equations out, and we trained on other classes, and we tried to find out if the algorithm is robust enough to be able to detect, for example, terms like the time-dependent terms, double derivative of time or single derivative of time, and things like that. And to design that, we created a lot of different features. For example, we got the fast Fourier transform of average consecutive subtraction, amplitude of vector signals, and symmetry of motion vector, as I described before. So to summarize this part, essentially you have this time-dependent data that you may get it from the satellite images, or you can get it from everywhere. Then what you do is that you take different types of feature. For example, you do feature extraction on time derivatives, and you do feature extractions on the spatial or space derivatives. And then you create a training using, XGBoost, which is mostly an ensemble / decision tree type of machine learning, and you try to assemble the terms that are relevant to these features. And in that way, as you can see, this is the accuracy of the prediction for us for the completely unseen class of equations. So these are the equations that are unseen. So what it means is that, for example, if you wanted to predict this upper equation, we trained it on the other equation, and we just tested on this one that the type of equation was not seen. Also, one of the things that is important to the mechanical engineers is that the domain knowledge. So if you only input the raw data, which we put it raw data as 21 by 21 by 21 as the time-dependent spatial data, we make a capsule here, a box, and then we did this, classification for understanding and actually distinguishing the partial derivatives. And look at this. We can see that the 3D CNN is not doing a great job, but as we are adding these hand-designed features by the domain knowledge of mechanical engineering, you can see we were able to boost the data from the raw data on even XGBoost to 99.77% accuracy on the unseen equations. So the story here is that the domain knowledge of mechanical engineering is very important in designing the algorithms that can be coupled with even shallow machine learning like XGBoost to boost their learning. The second topic that I want to go over is the topic of deep learning material discovery and the type of, again, domain knowledge that we use here. So if you think about it, current computational framework for detecting, for predicting material property is that you do a lot of density functional theory or molecular dynamics simulation, which are very computationally expensive. And sometimes, they fail to take the advantage of correlations and patterns of known materials. So the question is that can machine learning help us to overcome such kind of shortcomings there? And the most difficult part here is also finding out the descriptors or material representation. For example, for a crystal, how can I represent a crystal? So and then the tasks that are usually very temptable to predict in chemistry and material science is that, for example, you have the formation energy of these two crystals, and then you wanted to learn the connection between a structure, chemistry, and these, for example, formation energy. And after you learned, you wanted to predict it for the new material because you wanted to high throughput screen a large library of materials, because you can create hundreds of thousands of different crystals using different kind of arrangements of the molecules and atoms together. And computation for those is very redundant. So inspired by crystal graph convolutional neural networks that essentially uses the graph convolutional neural network on the crystal data, which uses actually basic atomic descriptors, we try to enhance or take it to the next level by introducing something called orbital field matrix into the features. So in which, if you remember in college or in high school, we were able to write, for example, each atomic element as a kind of descriptor, like, I mean, their valence, essentially orbitals. So what we did here is we created this orbital features, which is a 32 by 32 feature matrix, and we tried to connect it. We tried to create a kind of matrix of data for all these atoms in different arrangements. And then we added those type of data or features, and we call this algorithm orbital graph convolutional neural networks, in which we have multiple levels of features. For example, neighbor atom features, orbital field matrix features, and kernelized distance features, and basic atomic features. And so we rewired and we created a kind of autoencoders, because the number of features are exponentially went high. I mean, they are 1148. And then we created something like a nozzle-like autoencoder here, and we put it in order to recombine the features. And then we predicted the material. So we tested it on different kind of machine learning tasks. One of them, for example, is Prof's guys. I mean, these data sets are available on Material Genome Initiative, free of charge. And you can see that we were able to boost the accuracy of prediction, again, because of the reason of the domain knowledge. So we knew that adding much more, for example, orbital interactions between atoms will give much more knowledge of chemistry and the structure of the material. And that was able to do these significant improvements on different tasks. For example, you can see 45% on formation energy, for Prof's guys 50%. And that is something really important. So the third story is also how we can use this in control. So mechanical engineering is not only about system identification or PDEs or material discovery, but also some part of it about controlling and basically using it for manufacturing. So this is also a paper that we recently published in Additive Manufacturing. And this is about using laser, essentially deep reinforcement learning to control the laser power in additive manufacturing. So as you know, I mean, additive manufacturing is really important technology these days, that you can create parts with a lot of complexity. And also you can print alloys with a specific material or alloys that they are not possible with the subtractive manufacturing, because essentially the toughness and the stiffness of material is in a way that you cannot cut it. So additive manufacturing can be really, really cool in that aspect. And another aspect of additive manufacturing, which is really cool, is sustainability and clean energy. So, you know, I mean, it will reduce waste, and also it is much more energy efficient. So, but I mean, there are a lot of problems also in additive manufacturing. For example, one of the biggest problems is that when you are printing, essentially there is this melt pool, that there are overheated areas or underheated areas, and there are splashes or spatters that I talked about. And this causes a lot of defects. For example, one of the most classical defects is called keyhole, which is a porous actually blob that is forming inside the material. And those are not good. Essentially, those are wreaking havoc with, you know, I mean, the structural integrity of the part, or with the mechanical stability of the part. So the objective is that can we create a kind of like efficient control policy using AI, that we control the laser power or velocity in a way that we avoid these defects. So we avoid these defects, and at the same time print fast. So because scalability and being able to print fast is important. So in order to test this, since we need a kind of like emulator as Atari game, you know, we use Eagar-Tsai model for transient heat conduction. So we solved it, you know, I mean, this is the conductive Eagar-Tsai equation with a point source, as you can see. And there's an analytical solution that Eagar-Tsai came up with, which is beautiful here. And you can essentially move the laser pointer and we build the thermal. You can essentially do the thermal imaging of the scan pass during the manufacturing. As you can see, I mean, this is one example that we did, and you can somehow see this. Now, there is another important thing to know about additive manufacturing is that there are certain paths that they lead to defects. For example, if you think about this path, I mean, as you go inside this triangular path in the middle, you can assume that the heat is accumulating in the middle and there will be a huge blob of molten metal. And then that creates a lot of defects. As you can see here at the end, the melt pool depth is negative 100 micrometer. And that is not good. That creates a lot of porosity inside the material. So we thought, I mean, why not using reinforcement learning in which actually you have an agent which is interacting with the environment and it does an action, and then it is parsing out, I mean, a reward. So we thought that, okay, this is the environment of additive manufacturing in which you can use this emulator of Eagar-Tsai in order to simulate the environment. And then the reward should be consistency of the melt pool. We shouldn't see a lot of variations in the melt pool or essentially a huge temperature accumulation, which you can see this via a thermal camera. If you have a thermal camera and you install it on the machine, EOS machine or trunk machine, you can do this. And then you can develop a deep learning policy network, and the agent can change its power or velocity in order to maximize the reward. So the goal is to maintain a constant target melt depth. So this is the way that we engineer the reward. I don't go into the details in the interest of time. So you can say that, hey, I mean, this is the depth of the melt pool that I'm targeting or thinking about. So try to minimize this depth of the melt pool or try to minimize the standard deviation of that depth of the melt pool. So essentially the state space, so the elements of the deep reinforcement learnings are state space, reward, action, and the emulator or the environment and the agents that is working. And this is what it sees, you know, if you put a thermal camera instead of thermal camera, here we use the Eagar-Tsai actually model. So what you can do is essentially this will be your state space. I define the reward as the minimizing the standard deviation of the melt pool depths. And then this is the amazing point about AI, that you can go from, for example, thermal images to the control policy or moving of the agents, you know, I mean, so no mathematical formulation is capable of doing this, right? I mean, you give a bunch of images and you go and change the power or velocity of the laser printer. But AI, the good thing is that it's a universal function approximator. And also it takes any kind of modality of input like images and change it to a control command. So we use something called proximal policy optimization algorithms, and we tried it with A2C, which is the actor critic networks, and we benchmark different types of algorithms. And for example, this is the way that you can control the power using AI. So as you can see, this is the power. I mean, it is trying to change the power, and you can see pretty much a consistent melt pool depths, right? Because whenever it goes to the end zones and there is this heat accumulation there, it tries to actually reduce the amount of power. And here also in another effort, you can see the melt of depths, the depths of the melt pool is pretty consistent, but there are places that the velocity is a little bit changing. Also, we saw that there is a kind of like delay. I mean, there are still things to improve. For example, one of the big things that we try to improve is this delay and how we can use less number of images to make this real time, because controlling in real time is a big challenge still. So in the interest of time, this was the story about how AI can be useful in mechanical engineering. Obviously, we have a lot of different examples. All my PhD master students are working pretty hard, you know, I mean, to bring AI into different areas of mechanical engineering. But in the interest of time, I just went over 3 examples. And these are my PhD students. I mean, thanks to them for their great work. And these are the funding agencies that are supporting our work. Thank you very much, and I would be happy to take questions.
Thank you, Professor Barati Farimani. That's very wonderful and useful presentation to particularly students in here as well. And I also learned a lot from your talk. So you covered lots of, yeah. So we have about like 10 minutes for Q&A sessions. So I'd like to ask anyone in the floor here to participate in this symposium in person. I'm going to give them a chance to ask questions. So is there anyone? Yeah, Professor O.
This is Professor O speaking. Can you hear me?
Yes, yes.
It's very nice. It was wonderful talk, and I really enjoyed your speech. I have one question. I always have some problem collecting some data, and there is no guideline how to handle or how to produce and how to what is the proper amount of data we have to use. So do you have any guide or do you have any experience on that aspect?
Yes, that's a very good question. And it depends, to be honest with you, on the task that you want to do. For example, if you wanted to do drug discovery or a small molecule design, for example, for CO2 capture, or you wanted to design catalysts, data in those regions are very valuable, and there needs to be a lot of experiments. So for the data collection, usually for algorithm development, we rely on existing database and benchmarks. The other things that we are doing is we are using computation to generate the label. For example, if you wanted to calculate the formation energy, what we do is essentially we run DFT calculation or molecular dynamics simulations. For CFD, for example, we run CFD, but experimental data is very valuable, as you mentioned. And to address that issue algorithmically, we are taking two avenues. One avenue is data augmentation. We recently published a paper on how you can essentially augment the data for the chemical structures. And another avenue that we do is model developments that are working with less amount of data. So currently, a few of my students are working on contrastive learning or zero-shot learning, essentially, in which they need less parameters and less data to efficiently learn. And based on our benchmark, essentially on lower regime of data, like 1,000, 2,000 data points, they are really, really good and comparable to the deep neural networks with a lot of parameters and convolutional layers. So your question actually have multiple folds. What is the task? Is the data augmentation possible for that task? Is computation possible for that task? So I think, before collecting the data, we should ask these questions.
Right. Thank you very much.
Sure, my pleasure.
Okay, so then I'd like to give a chance to a participant who joined the symposium online, for those who are in this Zoom meeting. So if there anyone who would like to ask questions to Professor Barati Farimani.
May I ask a question?
Yeah, sure, please.
Yeah, hi, it's a very nice talk. I have a question regarding your system identification, which you identify PDE. I'm just curious, so how does the noise play a role in your accuracy of the identification?
That's an awesome question. So we have an upcoming paper. My PhD student Kazem is working on this. So we looked at the robustness of adding noise. So you can artificially add noise to these systems, right? And we added noise. You're right. There's a specific level of noise that you can add. Like we added more than, adding more than 5% noise based on the description we have is messing around with our algorithm. And robustness to noise is one of the big problems, because you are right. This data set is very clean, right? We computationally created this data set. And what Kazem did, in his second work, is that he added some noise, like 1%, 2%, and we we added more noise as we go on, and we wanted to find out where it breaks. And essentially around 5%, 6% noise it is breaking. And in another work that he's doing is trying to find out if these features are robust enough that even if you are adding noise, is it able to take care of, identification of partial derivatives?
Thank you.
And I have a following question on this slide as well. So
sure.
Here you're able to identify this system which consists of first or second derivative in the space and time. And yes. I'm just curious, how is your approach is also valid for identifying a nonlinear system? So here I'm looking.
Yes, there's another work that he's also doing, and that is for the nonlinear systems. I mean, we are working on the PDEs, which are both nonlinear and also stochastic. So stochasticity is one problem, nonlinearity is another problem, and then we are combining them. There are things that we are doing like integer programming, and I think Steve, in his talk, he will talk about the sparse regression and the SIMD, which is, they are finding actually they are doing system identification using nonlinear dynamics. We are also trying to find out the features, but the roadmap that we have essentially is to design the features that are robust. Like back to the previous question, noise is playing a significant role. If you add noise, and we know that experimental data have a lot of noise, that's inevitable. So that's something that we are actively working on. That's a great question, essentially, because that's an area of research, and it's open to all of us.
Yeah, that's right. Okay. All right. So I think we have just a few minutes for one more question. So is there anyone in the Zoom or on the floor who oh yeah, Professor Che?
Hi, it was nice talk. I'm Sungin Choi from GIST. I have some questions. I'm working on aerodynamic design optimization. And then when you talk about the data, we want to evaluate, aerodynamic performance or analysis. And then CFD takes a long time. Parallel computations with, many hours of costs, computation time. So in mechanics area, especially in CFD, getting a one data takes a long time, whether this is an experiment or a simulation. So, learning, right? Learning is very difficult in this area for the, directly applying the mechanics to the design. So do you have any recommendation? It's a very different types of the data, it has a computational cost. So.
Definitely, yeah. I think that's a very exciting question. I myself, in my lab, we are doing two avenues. So one avenue, as you mentioned, CFD, like other computational techniques, is very, very time consuming over HPC. It takes like days and weeks, to run a large scale simulation. So one of them is reduced order models, which we are actively working. We recently have a feature paper in physics of fluids, and we introduced deep learning based reduced order models in which you non-linearly reduce the order, and then you are able to propagate on the latent vector. So that's one way. Another way that we are actively working on is called super resolution. I don't know if you heard about super resolution or not, but if you think about images, you have these blurry images and you have high resolution images. And there are techniques in AI using generative adversarial networks and autoencoders and units that you can go directly from a blurred low resolution images to high resolution images. So you can think about the CFD calculation at low resolution or very, very coarse mesh, that you go to a fine mesh by learning this complex manifold of going from low resolution to high resolution. And we have a paper on arXiv, which is under review, and that's about, for example, you can go from LES, which is the large eddy simulation, which is lower resolution compared to DNS, to the DMS. So you can learn this mapping. And I think, I mean, that mapping can be learned in a lot of computational fluid dynamic or even finite element analysis in solid mechanics. So I think, I mean, there are two active areas of research in order to speed up computation. One of them is reduced order models. Another one is super resolution. Two keywords.
Yeah. Okay, I think those areas are pretty active in CFD area as well.
Yes. Yes.
Okay, thanks. Yeah, thanks. It was a wonderful talk.